My name is Yevgeniy Dodis. I'm a professor of computer science at New York University. I'm specializing in the field of cryptography and information security. I've been working in this field for, I guess, over 30 years now. And I specialize in basically all areas of cryptography, including secure messaging, randomness generation. Now I do a lot of work in post-quantum cryptography, but also encryption, authentication, you name it. And we're in my office in New York University at NYU in New York City. So we are sitting in a building which is called Courant Institute of Mathematical Sciences. So this institute includes the Department of Mathematics and part of the Department of Computer Science, mainly theoretical computer science. So I'm part of Department of Computer Science, but because I work in cryptography, which is considered theoretical computer science, well, although it's also applied, I am part of Courant Institute, which is a special institute dedicated to basically mathematics, applied mathematics. So theoretical computer science is considered applied mathematics, basically.
Okay. You work in post-quantum cryptography already,
Right.
so do you work on a specific algorithm?
Yes, so the specific problem, I'm interested in several algorithms, several questions. Well, I guess more generally, quantum cryptography, there are two, relatively complementary but equally important aspects. One is how to protect existing, so-called classical cryptographic algorithms. Again, is a threat of, hypothetical or not, but a threat of quantum computers. That's called post-quantum cryptography. And then there is real quantum cryptography, which is if good guys actually can have access to quantum computers, can they do more than with traditional computers? So I actually work a little bit in both, but I would say probably the most prominent direction is post-quantum cryptography, and specifically I'm extremely interested in developing post-quantum secure messaging algorithms. So for example, applications like WhatsApp and Signal, Apple Messages, and so on, they all use what is called end-to-end secure encryption. So it means that even the service provider, whether it's Google, Meta, WhatsApp, and so on, even they cannot read your messages. They help you to exchange messages with your partner, communication partner, but they cannot read your messages. And unfortunately, because it's already non-trivial to build this what is called secure messaging applications such as WhatsApp, they use cryptography which would be broken by quantum computers. So there is a big challenge to make it post-quantum secure in a sense that this is already widely deployed. Billions of users are using it every day, and post-quantum cryptography is slower, currently noticeably slower. We're talking slower, I don't mean necessarily only the speed, but everything, communication, key sizes, everything is kind of bigger. So right now you have a lot of people using something which is fast and it works, and it's very challenging to tell them, okay, now everything will be like 70 times slower, right? In practice, people don't do it, so it's a very challenging task to build post-quantum secure messaging applications.
The fact that we still utilize that particular math assumption, because after all, it really ends up to be about that, and is so largely used. Everything is based on that so far. Is that a risk, or maybe we shouldn't have only rely on that particular way?
No, it's a very good question, and it's also a very controversial question. The opinions, and it's also a question where people's opinions shift over time with the development, with more knowledge that we have. The common wisdom right now is quantum computers are not an imminent threat, but it is getting more and more realistic that they might be, eventually be built. I don't know in how many years. This is people disagree on the number of years. Most people agree it's not going to happen in the next probably like decade or something like that. Some people maybe disagree with it, but majority of people agree. Still, it is, quantum computers is advancing. Google and other actors, China, they are, able to store more and more qubits. They cannot really do meaningful computation on these qubits yet, but, they're claiming to various extent, but definitely they're extremely far from breaking anything like RSA in practice these days. But right now, even the skeptics, they cannot ignore those advances. So definitely it is getting, I don't want to say dangerous yet, but it is definitely riskier and riskier to use it. So the world has to be prepared. And in fact, National Institute of Standards and Technologies, NIST, they have developed this program. They have this post-quantum competitions. There are already several winners for signature encryption schemes. And recently, they even passed a resolution. I believe then, I might be wrong exactly in the years, but I believe by 2030, everything should be post-quantum ready. So everybody should be able to offer post-quantum solutions in addition to classical solutions. And by 2035, you're actually not allowed to use things which are not post-quantum secure. Whether they're overreacting or not, the opinions are, mixed. But the hope is that by 2035, somehow post-quantum cryptography will become so efficient that it's just maybe not going to be an issue. In a sense that right now people are worried, it's like, well, I'm going to lose like a factor of 70 for what? It's like unclear. Everybody's going to suffer for something that may never be built. But they give enough time, like right now, like 10 years until this has to take effect. Hopefully we'll know more. Either it becomes non-issue, post-quantum crypto will be like so fast that it's just, people will just switch to it. Also, there is the other danger. Classical crypto systems, sure, they can be broken by quantum computers, but RSA is a classical assumption. Again, as classical computers has withstood the test of time. New post-quantum assumptions, they're getting more and more mature, learning with errors specifically. That's the assumption that is one of the more popular assumptions for building those post-quantum crypto systems. But this assumption, it's getting close to 2 decades since its introduction. The person who is my colleague Odette Regev, who introduced it, won the Gödel Prize for it and Test of Time Award. So, but it's still newer. It's like 40, 50 years, maybe 30 years, less studied than traditional thing. So there is actually a conceivable danger that maybe it's not even classically as secure. Forget about quantumly, just because it's a new assumption. But many people are getting more and more comfortable with this assumption. So as a result, basically the current recipe that people suggest to use is the following. First, we are slowly going to switch what is called hybrid cryptography. So we're going to take a bullet. We're going to basically design a crypto system which is noticeably slow as the existing crypto systems, but it is secure as long as, it is secure against classical computers if, let's say, RSA or discrete logarithms are secure. So you're not just going to throw them out right away and replace them by post-quantum analogs. So you're kind of going to use both. So you kind of intuitively encrypt message twice or something like that, or sign message twice. So intuitively, if somehow this quantum assumption turn out to be not as secure, we are still as secure as before. We are not like losing anything by switching to something less studied. But if quantum computers are built, we are also secure. So it's kind of a win-win situation. Well, except it will be, at least twice, but probably much more slower because you have to implement both.
What about post-quantum, and actually you are saying even quantum cryptography, that's how you call it after all. So we know all the work by NIST that they've done so far, but what else, especially internationally, in terms of like setting some standards, keeping researching, because we even don't know how safe these are, and the fact that NIST are actually, is not in a good situation right now, right? So, I mean, do you know any other organization, international or maybe European, that could help?
That's true. Yeah, I forgot. So Germany, I think the equivalent of NIST in Germany, I know they gave a talk at Real World Cryptography Conference. So they're definitely involved and they're doing something. Of course, there are a lot of individual researchers. Personally, I mean, I have like mixed feelings about these competitions. I do think, the word of NIST, I think it's really important and it's great that they're doing it, that they're systematic. But the problem is it's not like a magic wand, right? It's not like, I know people in NIST, they're wonderful researchers, but, partially because they have other responsibilities, in the world of kind of, cryptography, they're not necessarily the top of the top researchers. They're good enough, they can do like really solid work in standardizing or whatever, but the top researchers are usually in maybe research labs, private universities like NYU, whatever, MIT, and so on. So it's not like, oh, if NIST kind of approves it or whatever. They have their flaws. They made mistakes. A couple of times they approved something that was later broken. So it's not like, oh, NIST is doing it. It's automatically secure. In fact, the good news, they're collaborating with all of us. So it's, there is a process, and, anyway, we all make mistakes. But I think so. I think it's great that they're involved. So definitely, I know in Japan there is a lot of interest in it. In China there is interest, we just don't know. It's like not super public what they're doing. So definitely there are fantastic researchers in France, in Germany, in the United Kingdom working on this. So yeah, I'm just not exactly familiar with the organizational standards. So some who NIST kind of de facto assumes a role of leaderships, and everybody so hopefully believes that the process is not corrupt, and indeed everything is with public discussions, public forums.
We relied on RCA for more than 50 years.
50 years now.
And that was what allowed to grow in this digital economy and everything else. And without the RSA, it probably wasn't even possible where we are now. And now with quantum, if you don't have a standard or a safe communication, in fact, they also talk about the quantum internet and
of course, quantum key distribution. There is like a lot of work, as I said, in quantum cryptography. There is exciting work. It's a little bit more theoretical now, just because, as I said, quantum computers don't yet exist, so we can write all these papers, and who knows which of them are realizable. Roughly speaking, in quantum cryptography, if this is what you're asking, there is this divide which hasn't been really kind of formalized, but people in the field know. So things kind of something called quantum key distribution is somewhat practical on short distances. You can have like two devices that never met, basically, and agree on a key which is secure as long as they solve the question of authentication. So they basically reduce the question of privacy to the question of authentication, which is pretty cool. But yeah, once you have like authenticated classical channel between two parties, but the problem is there are many more amazing things we know how to do in theory quantum, but those things require you to do there is no unified terminology of this, but basically operations on multiple qubits. Once you do this quantum key distribution, the amazing thing about it is basically you just send a bunch of independent qubits and do operations effectively on single qubits. And right now, quantum storage is like we don't know how to store things for a long time without like destroying it quantumly, the qubits, and we don't know how to do computation on kind of multiple qubits without, in practice. In theory, we do. In practice, we don't. So who knows? That I think is more long term, and in fact, I know a lot of people, including NIST, I think, they definitely don't recommend to invest in QKD, in this quantum key distribution. They feel like it's in practice going to be less secure than the classical one. I don't know if I 100% agree with it, but definitely I think there is no reason to. There is a good reason to invest in QKD and make it more and more practical, but there is no reason to panic right now. I think the world is, is okay the way it is going. We are basically exploring all directions in parallel. Breaks of, this post-quantum assumptions, everlasting privacy, better assumptions, more standards. So I actually think we're in a pretty good place in the sense that things are developing. I would actually say, but maybe it's like a little bit of a selfish thing in the sense that this is the area that I worked the most and I see challenges. I actually think the main challenge right now, in the sense that we should continue doing all this amazing work, the main challenge right now is to transition to post-quantum thing without people noticing too much. Because right now it's like if every time I send like to you hello, it will take like a second for you to get. Maybe a second is okay, but instead of a millisecond, a second, it's people notice, right? It will say, wait, it's like why somebody? It's like I'm typing. Now you click a button, okay, switch to post-quantum, and now everything is coming to a standstill. It's like everything is super slow. So I think this, and this question is not purely engineering. There are like clever algorithms, like for example, my work with Signal, we developed this thing called, so Signal was using the algorithm called double ratchet. Never mind what it is, but it was like a really clever algorithm to continuously refresh keys to make the secure messaging very secure, but it was based on discrete log kind of assumption. And we're adding the triple ratchet, we're adding this post-quantum ratchet, like the third ratchet to the Signal protocol, which is everybody's using WhatsApp and so on. And this thing necessarily, it is like 17 times bigger, but we're doing pretty clever techniques using error correcting codes to make this thing still very practical, maybe like, I don't know, a factor like literally 2-3 slows, and currently it's done, but still give you meaningful post-quantum security. It's not going to be instantaneous. It's like in 2 messages we recover from compromise, maybe in 50 messages we recover from compromise. But at least, so I think this engineering questions, how to transition what we already know to practice, so people are still happy and not complaining. I actually think, at least short term, that's the biggest challenge. Long term, of course, we should still do all those amazing things that we do in developing both quantum and, I would say post-quantum is more important. Well, sorry for my quantum friends. I mean, more important meaning for real world, kind of. For science, both I'm like super fascinated by both of these branches.
Yeah, the problem though is not just messaging. There are so many applications out there, including hardware, including you know, the backbone of the internet, the switches and so on, including all the data centers. Imagine if you can break, you know, inside a data center of Amazon. Like there is so much stuff in there, you know, that for everyone, people out there. But then all the infrastructures, the airports, the transportation, public transportation, the national security. I mean, there are so many, and then also just, you know, application in the hospital, like, you know, from the device to the software to the layer to the protocol. There's so many things that needs to be updated. So even if you like come up with a very good post-quantum algorithm, the time you have to have implemented in all these millions of type of applications, and also not just the application, but what is inside the application, the protocols, again, everything. It's going to take, I don't know, 10 years, probably.
No, you're right. It's like in some sense, it's kind of maybe similar in this, whatever, year 2000 problem that people were thinking that the, you know, millennium would switch and the world would come, but somehow we survived it. I mean, this is much more challenging. I agree with you. And you're right, there is a lot of people working in different ways to mitigate this problem. So, you know, the most obvious one, okay, we developed this post-quantum standards, let's switch, you know, TLS, transport layer security, secure messaging, let's make it post-quantum. A lot of engineering challenges like this triple latchet protocol and so on. You know, there's one direction. Another set of people believe in this secure hardware. They can say, listen, let's try to minimize reliance on public key cryptography. Fine, we make more assumptions, but like, for example, even Apple, the way Apple approached, like, you know, in the area of secure messaging, they said instead of symmetric authentication, which is kind of built into this secure messaging, they're replacing it like by digital signatures, which are like slower, a little bit slower, like Apple for their messaging. But they say, but the problem is we're like, these signatures are done by our enclave. So the messaging is actually done in kind of, you know, secure memory, but it's still kind of in memory. And the signing key we can put, you know, Apple gives like, you know, a way to people to do a limited amount of operations in the secure, you know, enclaves or in secure kind of processor inside the phone. So therefore they can say, listen, we are basically saying even if you steal the state of the secure messaging application, you're unlikely to steal the secret key because it's sitting in this secure thing. So therefore we actually doing something which is theoretically less secure, theoretically, but we bet on the fact that you're not going to break this hardware. And a lot of people are putting more and more things in secure hardware for this reason, so that maybe you rely on less of public key cryptography and just put trust in this.
Another solution could be also make the keys differently. So the keys are not made by factoring numbers, but actually made through post-quantum algorithms. But then even if it's just replacing the keys, then you also need to replace the algorithm that
of course,
crypt and decrypt it, right?
Well, that's exactly what the post-quantum computation is. So MLChem, which is like the new standard, that's what it is. It replaced, you know, the RSA or LGML kind of encryption. It replaced with or RSA encryption. It replaced it with this new thing based on different assumptions, based on different assumption lattices. So yeah, so it's definitely one. So one way, basically, I see kind of three complementary ways. One way is like it replaces algorithms, but you know, of course, these algorithms are new. Maybe they will be broken by something else, possibly even classically, right? Like some people work, I don't believe they will succeed. Some people, this new assumption for post-quantum encryption, you know, this modular LWE assumption, whatever, some people say, oh, let's give it to AI. Hopefully, like, you know, ChatGPT will solve it. So far it failed, and I believe it will fail. But they say, okay, so, but you know, but some people believe it. So they say, okay, we don't believe it will break RSA, but there is a set of people that believe that they will break these lattice assumptions. You know, there is a way to break it without breaking RSA. You know, cautiously disagree, but I don't know. Obviously, people know it's like it's part of your beliefs. But yeah, basically one way is to replace the algorithm. The other way is to distribute trust. The other way I already said is like to rely on the secure enclave. So basically, there is a trusted party that does like limited amount of operation, and then maybe you need to rely on less of public encryption because you still need something, but maybe by putting more of those trusted parties, you don't need to transmit so much data and so on. This is kind of another technique. And the last one, which we didn't talk about it, in theory, that's the best one. In practice, it's for multiple reasons, like lagging hugely behind, but this is called multi-party computation. And this is like, there are a couple of players, like Coinbase is kind of blockchain company, well, not blockchain, but, company helping other blockchain companies store their wallets and so on. So the idea is instead of storing some secret information in one place, you kind of store it on multiple machines in a way that even if you compromise one or two machines, or like, break some encryption scheme originating from one of the machines, you need to break all three of them somehow, right? So it's kind of distributed trust. Still, those schemes, largely rely somewhere if you kind of observe all the communication and break all the encryption schemes, it kind of maybe doesn't help, right? But at least it becomes much harder. But now, basically, by distributed trust, it's not like currently. You like observe like one ciphertext, you take it to the lab and spend 50 years. Now you need to be like practicing. Say, wait, I need to get something thrown here, something thrown there, something there. I need to combine them. I don't need to miss it. So this becomes in practice actually really hard. And then you go, I miss this like little ciphertext. Oh, now it's too late. I can break everything here. I still don't know what the message is because you kind of need this like a jigsaw puzzle. You need all the pieces to do it. So in theory, this multi-party computation should work. We've made tremendous advances to make it more practical. But the problem is it's hard to explain it to consumers. It's hard to explain it to companies. It's hard to like give the software which is easy to use. It's I believe it's actually might be practical enough, but somehow this encryption, it's somehow because it's like a local thing, you just kind of install something on your computer and it kind of works. Here you need coordination with multiple parties. It's just, but I don't know why. In theory it should be great, but this multi-party computation is severely lagging behind. It's barely used in the real world, for reasons which I don't understand. But yeah.
Let's say that it's not even about the quantum computers, or maybe it's going to be a quantum computer, but more is like the research around quantum. And you're a mathematician, so you know that the breakthrough actually could be not in the computing, but actual in math in a way. And that if there is a math that is discovering how to break the public key encryption, then you don't even need the computers.
Right.
And so do you think that could be a threat or?
Well, okay, so there is like, of course, a deeper question that essentially most of cryptography, and definitely public key cryptography, is not unconditional. It's based on assumptions. We usually could just say, okay, this is secure, bulletproof, it's like impossible to break, but we cannot do it, and there are big mathematical barriers to that. There is actually, I do want to say, there is a branch of cryptography which is a huge area. I should have mentioned it. A non-trivial part of my career and my research was about information theoretic cryptography. There is a branch of cryptography where under various modeling, you can get unconditional security. That's the best security. It's like not unproven. It's like a full bulletproof theorem. But those results are limited. They're still amazing, but they're limited. Like you can authenticate a message only once. So you can encrypt, limited amount of information with perfect security at the cost of pre-sharing on a long enough secret key. We can encrypt, but there is, the shining possibility that if you want to encrypt like 1 megabyte, you need like 1 megabyte of pre-shared key. But for authentication, it's not true. There are better bounds. So there are definitely things we can do unconditionally. It's a huge, there is something called secret sharing, multi-party computation. There are a lot of things that you could do under various modeling assumptions. You have to be careful unconditionally. And I'm like super excited. There are a lot of things that I worked on. For example, I introduced with my former student Daniel Vick something called non-malleable extractors. It's an information theoretic object, and it was a critical part of a paper that just won the Gödel Prize this year in the whole of theoretical computer science, right? Which is like the big prize. So some advance in cryptography was important to build like a new type of, never mind what it is, like something called randomness extractor, which we didn't know how to build before. So somehow this cryptographic thinking, and in particular unconditional cryptography, was useful useful outside of cryptography, just in complexity theory and more generally theoretical computer science and mathematics, to do something we didn't know how to do before, like build Ramsey graphs and so on. But the cryptography that people like to use is just, you never met a person you agree on a key. It's called key agreement, or like public key encryption or digital signatures. Those things which are very much more convenient, they require computational assumptions. At the very least, to solve them, we need to solve this really famous problem, like to separate P from NP. This kind of, it's one of those Millennium Prize things. So it's unlikely we'll build it unconditionally. So in this sense, this, I'll call it super convenient cryptography, does require assumptions. So everything is based on assumptions. And the question is, do you believe in these assumptions or not? And here we have a lot of results. You would say, well, you use a belief or not, but somehow we developed a lot of techniques. Some assumptions are better than others. We kind of can separate. We can say, okay, digital signatures, they have a well-defined meaning with respect to which we know the digital signatures are likely easier to build than public key encryption, which is easier to build than, I don't know, general secure computation, which is probably easier to build than something called obfuscation, program obfuscation. So we have this kind of gradations of different assumptions, including like number theoretic assumptions such that RSA. So we know a lot about relative kind of order of this assumption and what we believe, and people and even the algorithms, people kind of both kind of prove better and better, kind of, we call them reductions between different problems, but also like algorithms. So we have with time we get more and more confidence in some assumptions, but we are never sure, and most likely we will never be sure because these barriers, P versus NP, seems to be really hard barrier. Having said it, most people are extremely comfortable with the existence of public key cryptography.
Right. Too much, maybe.
Yeah, possibly too much in a sense. That's why I like to do information theoretic thing. I do want to mention one thing, which is probably not any, I bet not that many people mentioned that you interviewed. There is something called everlasting privacy, which is something was introduced a while back by Uli Maurer and Michael Rabin and slightly different, famous people in our field in different contexts. But philosophically, this is the following concept. You can say, listen, if you want unconditional security, it's in some settings it's either impossible or it's just too expensive, like somehow very inconvenient. There is public key cryptography, which would be really nice. We can do it, but that's maybe assumptions are a little bit too strong. I don't know, we're like worried about quantum computers or something. So, but we can do something intermediate. This is called everlasting privacy. We can make the kind of a distinction between the amount of time that good guys need to use something, let's say decrypt a message, decrypt a ciphertext, or bad guys, or for how long the message is secure. For example, typically you can say, listen, I send some sensitive information to like a general, I feel general, most likely it's only going to be relevant for the next, like to the good guy, to the general for the next like 2 hours, maybe 2 days or something. Maybe we'll need to decrypt it in a week again to see it. But after that, probably it's kind of, you already acted on this knowledge, whatever. But the ciphertext is, on the wire, a bad guy recorded it, and maybe it's a really sensitive thing. So maybe for good guys, you need it for a week or an hour, but for bad guys, it has to be secure for like 50 years, right? And for many things, there is this kind of gap. So everlasting privacy says, listen, what if we design a crypto system where basically the good guys, they only need to assume that for that week that they need this communication, something cannot be broken. You cannot break RSA, let's say, for this 1 week, right? But if you cannot break RSA for then 1 week, something changes in the surroundings, some information gets erased, and now you're secure forever. Right? So basically, it's kind of this kind of hybrid. So traditionally, if I want to do traditional public key cryptography, I would need to find some analog of RSA or something, learning with errors, which I believe will be secure for 50 years. And that's really hard. I don't know, maybe quantum computers are built in 50 years. But I'm confident they're not going to be built in a week. So I can use RSA. So if you use this setup of everlasting privacy, which is also slightly tricky, but if you use this everlasting what we call everlasting privacy, all you need to assume is like, listen, I assume that something will not be broken in a week. Quantum computers don't exist for a week, and then I'm secure forever. That seems to be like a pretty good compromise, at least to me.
Still rely on only one math assumption, and if that assumption is over, and in fact there is also price, so that's still there. It's still a question. It's just an assumption. It's a belief, after all, right? In mathematics. And so then the size of the keys, the schemes that you might use, that all of those that rely on factoring two large numbers
Right.
is all gone.
Right.
Right? And that's quite big. I mean, I don't know what, if you, let's say, if you do discover that tomorrow accidentally, what would you do?
Yeah, that's actually a fantastic question. It's kind of funny. At some point, you would think, it's like, okay, if somebody, finds a way to break factoring tomorrow, the world does that. But ironically, I had with my colleague, we were like, okay, let's assume just for fun, we were like just having a chat over coffee. I was like, what did you do? It's actually, I mean, it will be bad, don't get me wrong, but it's not, there are a lot of safeguards which are not digital in our things. You say, okay, I'll steal the money. Well, but there is still police. If you somehow, you out of nowhere, you build a mansion, people will notice. So it's actually not, I mean, it is very bad, so a lot of things, but it's not, the Ravens, this movie, somebody found a huge suitcase with money and then they don't know how to spend it because anytime, so there are a lot of safeguards around it, so it's not, I don't know, you can start taking records, you can start, I mean, there is something you can do, so the world is not going to collapse, it's not going to be apocalypse, but yeah, it will be pretty bad, and that's part of the reason that NIST is, telling us to deprecate these algorithms. But having said it, it's not, you're right that most of the world relies, actually there is less and less reliance on RSA, but, discrete log, which is kind of, in a classical sense, somewhat different algorithms, but for quantum computers, the same algorithm kind of, effectively breaks both discrete log and factoring. But yeah, you're right. Most of the practical things are using discrete log-based crypto systems, so, related to kind of factoring things. But, post-quantum computation introduced now this learning with errors. Now there is at least two. In fact, there is code-based cryptography. They kind of standardize HQC, kind of another encryption based on a different problem with coding. In signatures, we have all this multivariate, something called multivariate cryptography. So you're right, people are worried, and we try to diversify things. So right now, instead of saying, okay, this is a fastest, let's just use this, we kind of try to diversify a little bit. Even though in symmetric cryptography, for example, you may be heard AES, people are relatively comfortable with advanced encryption cipher. So you can ask the same question. If AES is broken, I mean, we have millions of alternatives, but, so there is both advantage and disadvantage of relying on the same assumption. The advantage is everybody is incompatible. Everybody has the same implementation, so it's kind of, it's easier to talk to each other. The downside, you're right. If this is broken, a lot of things have to change, but we have to be prepared. So we just need to implement different libraries. Sometimes, actually, for TLS handshake, people have options, what algorithms I like, and as long as you find an intersection, we can do it. So this I'm less worried about, in a sense. We definitely should develop more assumptions. And also the way we work in cryptography, there are two kinds of results, positive result building schemes. We can either build things like a concrete system on concrete assumption, like RSA signature or something like that, or DSA signature or whatever, some particular signature encryption algorithm, and reduce it to specific number theoretic assumption. But also there is a branch of cryptography where you say, hey, I just need to use any public key encryption scheme. I don't care whether you implement it using HQC or MLCAM or LGML encryption or whatever it is. You can just plug in anything you want and it works. And a lot of our results, generally, if the result is relatively nice and efficient, it's better to modularize it. So we like to modularize it. We don't like to give you one system and then one building block is broken. You're kind of, you have to start from scratch. We give you a modular thing and say, use any signature scheme. You don't like this, replace it by MLDSA, whatever, you suffer the consequences of efficiency. But yeah, we try to do things in a general way, but at the end of the day, you're right, at the end of the day, you need to believe some assumptions, and, if this is false, I would say the world is not going to collapse. We have enough alternatives to adjust. Right, because we have enough still physical, maybe we give everything to AI, somehow maybe it will be a little bit harder, but there is still enough physical kind of guardrails and kind of prevention. And as I said, it's actually kind of a fun exercise. I would love to see actually a movie. Maybe, if you know some people, I would love to collaborate with them. It's like, hey, you can, have a plot where you break RSA and see what you can do in the real world. I'm actually not sure. You can probably become rich, but it will be kind of tricky. It's not going to be like...
This is the movie.
Yeah. No, but I'm saying it's like you will have to hide it or whatever, do some money laundering or whatever, but... And here is maybe the last reason. If you look at cryptocurrency world, they're concerned about post-quantum, but they're not switching, right? At least not yet. So somehow the world of money, markets tell us that it's not time to panic. So I don't know.
Yeah.